So hello everyone, today we'll be having a small contest discussion over weekly Leetcode weekly 503, which I failed to attempt. Okay, because it was uh, not possible with the schedule I had. It was quite in the morning, so it was not possible. So I have tried this question, unfortunately, but I somehow submitted a wrong answer. So technically, I still don't know the answer. None of the questions are previously solved by me. Okay, so this would be the first attempt of mine to like a proper attempt. So we are given a sorted integer array nums and an integer k, return an array such that each distinct element appears at most k times while preserving the relative order of the elements in nums to preserve the relative order, and it's a sorted array. So one good way of doing this would be take a map. Like this is the brute force which I'm telling you. Okay, this is the brute force which I'm telling you. It's not an optimal solution to store the frequency. This would store the frequency. And what I would try to do is, let's take a test case. 111 223 and the frequency map of this would look like 1 2 3. This would be 3, this would be 2, this would be 1. So if a frequency of something is greater than 3, sorry, greater than 2, because k equal to 2, k is equal to 2, I would place it only 2 times. Answer dot pushback twice. And since I need to preserve order and this is an unordered map, this would be an unordered map. What I would do is, I would first keep a pointer I here, and I would check its frequency. I would twice, like k times, push it into array, an array named answer, and now answer dot back is equal to 1, right? Answers back is equal to 1. The last pushed item into answer is 1, and I would be here, I would be here, I would be here. Because it's equal to answer dot back, we would do nothing. So if I equal to answer dot back, just continue. Okay, now here I is not equal to answer dot back. Now take its frequency, it's 2, so push it twice. Now answer dot back is this one. I equal to answer dot back, skip. I not equal to answer dot back, here frequency of 3 is 1, so push it only once. If frequency is less than k, push it as many times as it occurs. Okay, fine. So this would be the approach with an unordered map. Now coming to, but we didn't use this property of being sorted, right? So if you have solved some problems like remove duplicate elements, etc., which uses 2 pointers, the same thing we would be doing here, which is using 2 pointers. So what I would do is 1 1 1 2 2 3. I would take a read pointer and a write pointer. That's how you should work with 2 pointers. If you have solved some other problems like remove duplicate, some sorted array, or in general some sorted array problems, use this kind of technique. You take a read pointer, you take a write pointer. So the first k elements, however, I won't be changing. So the first k elements won't change, right? Because yeah, even if they are this way, like the first k elements are this way, 1 2 is the first k elements, because if the frequency is less than k, still you keep them as many times as they appear, so they won't change. If the frequency becomes greater than k, these 2 elements won't change. From here you would start writing some other elements like 2 something, so the first k elements won't change. So writing begins from here, and similarly reading also should begin from here. So if this thing is already equal to 1, how can I check this? How can I check if it's already equal to 1? So if this thing is equal to write minus k would be here. If it's already equal to 1, then this is the place you need to write. Until you write till here it's already written. Nothing can be changed here. So until you write this blank, you can't move the right pointer from here. Now let's read the next element. Read. Okay, read pointer got updated. Now we are reading the next element. 2 is not equal to write minus k. That means 2 should be written here. 2 is not equal to write minus k. Write minus k. Write is this, write minus k is this. 2 is not equal to right minus k. That means you should write 2 here. Next. What is next? Now this place is written. Now you need to write something here. So the right pointer is here. Okay. And the read pointer also gets updated. So when the read pointer gets updated, sorry, read pointer should be here itself, right? First we need to, no, okay, read pointer gets updated. Write is here, read is here. So write minus k would be equal to here. It's not equal to read. So you write a 2 here. You write a 2 here. Next. The right, now till here everything is written. Till this point everything is written. Now right pointer should be here. Alright. Right pointer should be here. When right pointer is here, tell me, right minus k is 2. You need to check here, not this one. You need to check here because this is the recently written one. We have updated the array. So this is read is equal to right minus k. So something should be written here. We don't know what. Next, move read here. 3 is not equal to right minus k. Right minus k is this one. 3 is not equal to 2. That means you should write 3 here. Now 3 is already here. That means we need only till this part. We need to resize the array. So if I simply write a code for this, int n equal to nums.size and for int r equal to k, since we are starting to read from k, r less than n and r plus plus, right pointer is initially at k. If nums of read is not equal to nums of right minus k, that means you are supposed to write something on the right pointer, which is nothing but nums of r, and move right to the next position. Fine. Now otherwise the read would be just updated as it is because it's independent, it's in a separate loop, it would get updated. Now you need to resize this nums to nums.resize to right and just return this, return nums. That's it, a simple problem. Yeah. Done. Okay, I've already told you that I have, wait, am I getting recorded? Yeah. I've already told you that I have given a wrong attempt for this. I was solving for fun, not in a contest. So I was submitting something random. Okay, so whatever. Let's read this question. You are given a string password, strength of password is calculated based on following rules: 1 point for lowercase, 2 points for uppercase, 3 points for numbers, 5 points for symbols. Simple thing, right? All you need to do is, and each contributes at most once. So if you're given some password, let's say you're given a password, a random password, this one, push it into a set. Only the unique characters would be there, like b, b1, hash, these kind of things would be there. Why are we pushing them into a set? Because each thing can contribute only once. Even if there are 2 b's, you can only consider this strength as 1. Fine. So that's why we are pushing it into a set. Now we will iterate over this. We'll iterate over this one by one, and if it's a lowercase, add 1. If it's an uppercase, add 2. If it's a number, add 3. If it's a symbol, add 5. Pretty straightforward solution. So coming to this one. Initially I thought of a very bad idea. I was like, you just need to rotate and sort, right? So okay, first let me read the question for you. You are given an integer array nums of length n, where nums is a permutation of the integers from 0 to n minus 1. You may perform only the following operation: reverse the entire array, or left rotate by 1, rotate left by 1, and you need to sort it and tell me how many operations did it took you, the minimum number of operations. So initially I was like, either it would be sorted, either it would be rotated. So my logic was simple, but it didn't work. However, if it's already sorted, return 0. If it's rotated, then return 1, because to rotate it again you would take one move, and after reversing, if it's sorted, then return 1, because it took one move. If after reversing it is rotated, if after reversing it is rotated, you need to reverse it as well as rotate it, so it will take 2 moves. So it's a very bad idea, because it doesn't handle all the cases properly. You can check by yourself. So we need to think of some other idea now. So the thing is, if you are dealing with something which is either reversed or rotated, can I say that it would always be in a cycle? It would always be in a cycle. Either it would be something like 0, 1, 2, 3, 4 this way, if it's somehow rotated. If it's left rotated twice, it would become this way. Like initially it was supposed to be 1, 2, 3, 0, 1, 2, 3, 4. When you move it here, 1, 2, 3, 4, 0. Then after this 3, 4, 0, 1, 2 this way. When you move this here and when you move this here. Okay. 1, 2 would be reaching here, and yeah. So even if I reverse it, then rotate it, it would form a cycle. So how about taking this as either you would have a forward cycle, or either you would have a backward cycle. So this is a forward cycle. Okay, you're moving forward. Or you would either have a backward cycle. Let's say if you reverse this, what would happen? 2, 1, 0, 4, 3. So 0, 1, 2, 3, 4. This is a backward cycle. You're moving backwards. Okay. This is a forward cycle because you are moving this way. This is a backward cycle because you are moving this way. Fine. Either you would have a forward cycle or a backward cycle. If there's a forward cycle, there are two chances you have. Either simply either it would be by left rotating stuff, or else it would be reverse plus left rotating stuff. Let me kind of explain you, but before explaining I should find a proper test case for this. Okay, let's take it this way. I won't take any numbers, just visualize it. Let's say 0 is here. We'll take 0 as the reference because after sorting 0 would be the first number. So the thing is, it would either you would left shift it by some indices. Some greater numbers would be here. Let's say 0, 1, 2, 3, 4 is here. You would left shift it. 3 would reach here, 4 would reach here, and yeah, this part got sorted. Either this is one possibility, or else it should take you 2 reverse operations. How would it take 2 reverse operations? First, either you would let's say there are too many numbers here. Way too many numbers here. There are lots of numbers here and lesser numbers here. There are lots of numbers on your left and a little higher numbers here. Sorry, little lesser number of numbers here. Okay, the quantity of numbers which is to your right is lesser. So these many left rotations, it's hard. So let's say if there's 5, 4, 3, 6 5 4 7 6 5 4 3 2 1 3 0 1 2. If it's this way, if I just simply move towards left, if I simply move each of them towards left, what would happen? No, actually this is wrong. This should be 3 4 5 6 7. Sorry, my bad. 3 4 5 6 7 0 1 2. If it's this way, you are taking these many elements to your left, so these many moves you are making. Instead of this, if I reverse this, what would happen? If I reverse this 2 1 0 2 1 0 7 6 5 4 3, if I reverse this, now if I make left moves, 0 would be here, 7 6 5 4 3 2 1, and yeah, let's move 0 also. Here also let's move 0, by the way. Yeah, we have moved till here. If I reverse this once again, it took me 1 reverse move, 3 rotations plus 1 reverse move to sort this array. Okay, so this is equal to 5 moves. Here 1 2 3 4 5 6. Here this is equal to 6 moves. So these are the two cases which I need to handle. So first step, I need to check if it's a forward cycle or a backward cycle. So int n equal to nums.size. First thing, I need to find 0. 0, let's take 0's index as z. Initially -1, since we don't know which index 0 belongs to. I less than n, I plus plus. Now the thing is, if it's nums of I equal to 0, okay, z equal to I, and break. Fine. With this we have the index of 0. Now either you can have a forward cycle, so let's name it as f. Let's name it f. Okay, let us assume that forward cycle is true. Int I equal to 0, I less than n, I plus plus. Okay, if it's a forward cycle, nums of z plus 1, sorry, z plus I, what, if I take a cycle over it, like modulo n, if it's not equal to I, that means it's not a forward cycle. Because we are dealing with a permutation, this thing is true. Okay, so if the cycle starting from 1 is not equal to I, that means it's not a forward cycle. Fine. Now we'll mark this as false and break from here. It's not a forward cycle. Now we'll check if it's a backward cycle. What is a backward cycle? I guess I have already told you. Yeah, this is a backward cycle. So if you're in a backward cycle one, sorry, let's initially take it as true, and for in I less than n, I plus plus. Okay, if nums of, I hope you know how to traverse array in a cyclic manner. If z minus I plus n, it's basic modulo arithmetics. So modulo n. In subtraction, you basically add this plus n, not a big deal. If it's not equal to I, then it's not a backward cycle, and break. So no matter what, if it's not a forward cycle, and if it's not a backward cycle also, can I say that using the given set of operation, which is reversing and left shifting by 1, left rotating by 1. It is impossible to make it sorted. If it's neither a forward cycle nor a backward cycle, it is impossible. Fine. So yeah, this is it. And if it's a forward cycle, and the zeros index is 0, that means it's already sorted. So we need not do any kind of moves. Is that fine? If it's a forward cycle, that means after 0 it's 1, then it's 2, then it's 3, then so on. And zeros index, there's nothing in front of 0. Zeros index is itself the first index. That means this particular array is sorted, right? Okay, so we would simply return a 0. Next. Let's take int answer, which would denote our number of moves. And since we are minimizing, let's take int max. If it's a forward cycle, either the answer would be this way. Just by rotating it, we can just by rotating the elements before it, we can reach the sorted state. So it would be minimum of answer, the index of 0. That many places, till that many places you'll rotate it, isn't it? Here the index of 0 is 0, 1, 2, 3, 4, 5. And it took you 0, 1, 2, 3, 4, 5 rotations. So this way you can reach the sorted state, or else it would take one reverse operation initially. At the start you'll reverse it, then you'll do n minus idx. Sorry, what was the variable name for zeros index? Z, right? N minus z. Then once again you would reverse it, which would incur one move. And if it's a backward cycle, answer equal to minimum of answer comma. If it's a backward cycle also, you can rotate it by n minus idx times, or else you can rotate it, you can initially reverse it, then it would form a forward kind of scenario, then you will rotate it by index of 0 times, then finally you would reverse it once again. So these are the two possibilities when you have a forward cycle and when you have a backward cycle, and you would return answer. Okay, if I run this, would it work? Compilation error. Once again I wrote index. Done. Hopefully it should get submitted. Done. And it gets submitted. Fine. Clear? What are we trying to do? So if you are in a forward cycle, and zeros index is somewhere here, you got two options. Either you can reverse this and do all this stuff if there are more elements towards your left. Okay, this case is well explained, I hope. So either you can bring all the stuff to your here to the end and move towards left. That's one way. Or else you can reverse this so that maybe you can incur less number of rotations. Okay, and reverse it once again. So it would take one reverse move, some k rotation moves, and one reverse move. The k is basically dependent on your zeros index. Once you reverse it, zeros index becomes n minus idx, which is n minus z according to the problem which we took. So this k would be n minus z in case of forward rotation, and similarly in case of backward rotation, backward cycle, 0 would be here. You would rotate it either by idx times, n minus idx times, because because it's in a backward cycle, which means backward cycle means 0, 1, 2, 3. 0, 1, 2, 3. This whole thing should be a cycle, so 4, 5. No, wait. What was supposed to be backward cycle? Wait, let me write it. 0, 1, 2, 3. Okay, 4, 5, 6. This way, this is a backward cycle. Yeah, this is a backward cycle. So yeah, in this case, you have two options. Either you can n minus idx times left shift, rotate by left, because it's a backward cycle, or else after reversing you can rotate it z times only, and it will take a pre-reverse move and a post-reverse move. So I hope this is clear. Now let's move to the next one. You are given integer array nums 1 and nums 2 and a 2D integer array queries. So what are we given? An integer array nums 1 and nums 2 and a 2D integer array queries. Each queries is of the following types. 1 xy val, add val to every element of nums. So xy is basically the start and ending of the range. xy is basically the start and end of the range. Might be a segmentary question, isn't it? Is it a segmentary question? Next. 2 is you will be given total. Compute the number of pairs of jk such that nums of j plus nums of k is equal to total. Okay. So this is a pair sum kind of query. Can segmentary handle it? Segmentary cannot handle these kind of queries. Okay, segmentary cannot handle these kind of queries. Fine. So the add kind of query should work, and this kind of query should also work. Add query should work, this query also should work. So there's a technique called square root decomposition. If you have heard of it, there's a technique called square root decomposition. And as you know, CP techniques have fancy names and easy implementations. Okay, every technique has fancy name and easy implementation. Okay, so let us understand what exactly is square root decomposition and how it would help. One thing is clear, the brute force for this would be taking a range xy, taking the query xy. So iterating over queries would take q time. If it's a first type of query xy, to add something to x to y, it would take O of x plus y. And since you're doing it some q times, let's say all the queries are this kind of queries only, in this case it would take O of xy, and you're doing it q times, so it would take q into O of x plus y. And in worst case, this x plus y could be n, so it's q cross n. Then the second type of query, which is checking if the pair sum exists or not. So see, the query, there are two sum problem if you have done on Leetcode, which is the very first problem, I guess. There are two ways of solving it. One is sort it and use 2 pointers, or else use a hash map. use a hash map. This is probably the ways which you know and which are existent. Tell me which way would you use here? A general question. These kind of things are important because at the end, when you are actually writing some good level of softwares, you have to make sure that you don't mess up things by doing this. When you sort this, the original array configuration is lost. Okay, the original array configuration is lost. So after sorting, when again type 1 query comes where you need to add x to y, okay, did you get it? Why you would mess up? The ordering is changed. X and y would reflect to something else. So yeah, sorting is a bad idea. Hash map 1. Hash map 1. If you use an unordered map, it will take O of n space and O of n time as well. Fine. And this would appear q times. This query would appear q times. So it would take q cross n time. Now this is the brute force. The idea of square root decomposition is that what if I break this n into some blocks of size root n. So let's say there are numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9. The size of this thing is n equal to 9. Square root decomposition would break it into blocks of size root n, which is root 9, which is 3. That means every 3 things would come under a block. This is block 0, this is block 1, this is block 2. Fine. Block 0, block 1, block 2. So let's say now I want to add something to one of these blocks, add something to a range. Let's say add something to a range. There would be some logic which we would discuss later, by which if I'm given an index, I can know which block does this index belong to. Which block does this index belong to? We'll discuss this logic, how to figure this out, how to figure out which block does a particular index belong to. But let's say you are given a range L to R and you are asked to compute, let's say, a very simple thing, not this complex as the question. You are asked to compute something very simple, which is the sum from L to R. Let's say L is given as 0, R is given as 0, 1, 2. So L to R sum would be, you will be however storing the sum of these blocks. Okay, whatever is the required query, like let's say this is a sum query. Okay, this is a query related to sum. In these blocks you would store the sum. So you already have sum of block 0, which is 6. So if someone asks you sum of L to R and you already have block, you already have this block, so you can directly return 6. If L to R is here, you can directly return 6 plus, what is the sum of this? 9 plus 6, 15. 6 plus 15 is, sorry, let's say L to R is here. If L to R was here, you could directly return 15. If L to R was all the way till this block, then you could return 6 plus 15. Fine. So now the thing is, okay, you have told me if L is here, R is here, if L is here, R is here, if L is here, R is here. What if L is here, R is here? What would you do then? Or L is here, R is here. What would you do then? So I would say, if it's a partial block, if L is still here and R is somewhere till here, can I always ensure that if it's a partial block, the size of this part would be somewhere close to root n, or even I can say less than root n? it would be less than root n. This size would be less than root n. So even if I had to brute force addition this part, it would cost me somewhere less than root n. And if I had to brute force and add this part, like if I want to run a for loop 2, 3, 4, can I always ensure that it would cost me less than root n, or less than or equal to root n, or somewhere very close to root n. Okay. And due to a query, I had to encounter this situation where L is here and R is here. This part would be less than root n. This part would be less than root n. This part would be less than root n. So when partial blocks are coming, the thing is, you're always taking somewhere around root n. You're not taking a huge amount of time. And in between, let's say there's a block here. You know the sum of this block is 15. So you can compute this partial part, this part, and let's say this gives you some k1 sum, this gives you some k1 sum via brute force, which won't take you greater than root n. Okay, and this part is 15, which you already know. Isn't this very handy? The brute force which you're doing on these partial arrays, these partial blocks, is taking you somewhere around root n. So it's very optimal. And in between, if there are many blocks, let's say if it's this way, let's say there are multiple blocks, and if you are asked to calculate this sum, the sum starting from this block, the sum starting from this block, so this whole part you are asked to calculate. So calculating this thing is very small, okay, till this block end, it's very small, right? And the rest blocks would be directly added. The rest of the blocks would be directly added, like you already know the sum of these blocks. So isn't this very optimal? Can I say it's very optimal? So that's the basic idea of square root decomposition. Now let us understand how to apply square root decomposition here. I'll be coding and explaining at the same time because I'm comfortable that way. Yeah, so let's take some int n equal to, first let's rename them to some better names, x and y. So you need to apply operation on only nums2. You need to apply operation on nums2 only. Y dot size. And let's say b is the square root of n, and we take an extra +1 because, yeah, square root we need to find like the size would be should be slightly greater. Let's take it this way, square root of n +1. Okay, fine. Int k is equal to, because square root returns you an integer, if something has a square root greater than 2.5, something like this, ideally you should store 3 elements. So that's how it works. So how many k is the number of blocks. How many blocks can you split it? Can I say that I can, if each block is of size root n, if each block is of size root n, there would be ceil of n by root n blocks. So this would be equal to, number of blocks would be equal to, let's say we are splitting into k blocks, and number of blocks, which is k, is equal to ceil of n by b. So this expression is ceil of n by b. You may already know this, people who have solved cocoa eating bananas. Okay, so to answer these kind of queries, queries, which is add and compute if there's a pair sum existing or not. I need to store frequency of everything. I need to store frequency of everything. So let me make blocks now. I need blocks. We have already discussed an example of blocks which used to store sum. These blocks used to store sum. Now I need blocks that are supposed to store frequency. So each block would store frequency of elements in this block, frequency of elements in this block, frequency of elements in this block. That means each block would consist of an unordered map to store the frequency. Unordered map to store frequency, and we'll name it as blocks. How many blocks should we have? We need to have k blocks. We need to have k blocks. Let me have some water. Okay, we need to have k blocks. Now one more thing we can do is when you're adding directly blocks, when there are blocks in between, like in addition example we saw that we are storing the sum of these blocks, we are storing the sum of these blocks, right? But you can't exactly store two things at a time, right? You can't exactly store two things at a time. So what we'll be doing is we'll be storing a lazy array. Which would store the aggregates of these particular block. What do I mean? In simple terms, let's say one query suggests you to, there are some number of blocks, make this L to R. L starts from somewhere here, R ends from somewhere here. So this is a partial thing. Let's say it's this way. Now, if I want to update the frequency of these partial blocks, I can simply brute force. The way I update normal frequency, I would do it that way only. So these parts I can brute force. These parts, this part and this part I can brute force. But coming to the blocks, what's the purpose of brute forcing? It's again the same thing. What's the use of square root decomposition if you brute force here also? So what we'll do is we'll store the lazy of this thing. We'll store some lazy array of this thing. Lazy array would basically do lazy array size is k, right? So for k blocks, if you want to add a +5, the lazy of, let's say this is block number 0, 1, 2, 3, 4. So some part of 4 got added +5. Some part of 0 got added +5. Coming to this thing 1, 2, 3. You want to add +5 to this part. So instead of brute forcing, like every element, you need to minus the frequency of every element and plus the frequency of every element which has +5 added to it. Like let's say you have 4 here, you need to minus the force frequency, and you need to do f of 4 minus and f of 4 plus 5 plus. This is what you need to do, brute force in the sense. If you keep doing this for every block, it won't be optimal. Instead, you store a lazy array which would say that whatever the elements are there in 1, 2, 3 blocks, I have added +5 to it. We are ensuring this. So real value would be equal to stored value in we made a data structure here, right? Vector unordered map intent blocks. Stored value, whatever the value that data structure is storing, plus the lazy value. This is how it would work. Real value is equal to stored value plus lazy value. So remember this. I equal to 0, I less than, wait, what were we doing? We need to set the frequency of everything, initialize the frequencies. So how to compute the block number? You're having index I. You're having index I. Now I need to figure out if it's a 0, which block does it belong to? What's the block number? If it's a 1, which block does it belong to? If it's a 2, which block does it belong to? If it's a 3, which block does it belong to? If it's a 4, which block does it belong to? So on. I need to figure this out. So 0, 1, 2 would belong to a single block. 3, 4, 5 would belong to a single block. That means every 3 elements would belong to a single block. That means every root n elements would belong to a block. Can I say that block number is equal to, I can simply do I by root n. That would be giving me the block number, which is root n plus 1 actually, because here we are using root n plus 1. So this would give me the block number, like 0 divided by 3 gives 0, block 0. 1 divided by 3 gives 3 plus 1, 1 divided by 4 gives 0, 2 divided by 4 gives 0. So these three belong to same block. And also 3 divided by 4 also gives 0. Wait a minute. Okay. So wait a minute. Yeah, anyways, it's the floor division, right? By default it becomes the floor division, so this won't matter. So this is the thing, I divided by root n plus 1. I divided by root n plus 1, and root n plus 1 we are already storing here. So this thing would become the size of each block. Sorry, actually how it works is, let me give a better explanation of how this works. So when you do root n, sometimes you may also get 2.5, some values like this. That's why you are adding a plus 1. Okay, you are adding a plus 1, so that even if you get 2, due to 2.5 you get 2, this 0.5 however won't be present in integer, you somehow manipulate it to get 3. So the actual size is 3. So be equal to this thing. And when you do 0 by root n plus 1, it simply means 0 by, even if it's 2.5, do a plus 1, and that's how it would work. Basically it's 0 by b. Okay, block number, to compute block number you use the formula I by b. Fine. Sometimes I get confused because telling implementations is not that easy, but yeah, we'll implement block number is equal to I by b, and I need to update the frequency of this in this particular block, which is y of I plus plus. So in this block, update the frequency of this number. Fine. And we'll store our answer array. Like, to store the answers, we'll make this vector. We can't skip iterating through queries. Okay, we can't skip iterating through queries. So what's the type of query? It would be query of 0. So if type equal to 1, we'll do something, else we'll do something. We only have 2 types of queries. Fine. Now let us understand how would this work. In type 1 query, you'll have L equal to query of 1, R equal to query of 2, value equal to query of value equal to query of 3. That's it. Now you need to compute in which block does L and R belong to. How to compute it? We already know. If you are given an index, how to know which block do they belong? So L would belong to this block and R would belong to this block, isn't it? L would belong to L by B, R would belong to R by B. And if both of them belong to the same block, what you will do is L to R, because this, both of them belong to the same block, it is less than root n. In square root decomposition, the basic, the blind rule is, if it's less than root n, if it's somewhere close to root n, if it's small, do the brute force. How to do the brute force? I is less than or equal to R. If both of them belong to the same block, that means L to R, if they both belong to the same block and this block is of size root n, this block L to R would be less than root n, less than or equal to root n. So we can actually brute force this. So what I will do is, I will do blocks of start, which is the block ID, y of I minus minus. We don't have y of I anymore because we are adding some value to it. And if this blocks of start of y of I, if this becomes 0, this becomes 0, blocks of start dot erase y of I. Alright, and y of I plus equal to value and blocks of start of y of I plus plus. Fine. Or otherwise, if they don't belong to same block, one thing is, there would be a, to this block, if they don't belong to the same block, they belong to some different blocks. Let's say. If let's say L is starting from here and R is starting from here, I can do brute force till this point. So I need to figure out this point, which is left end of this left block and start of this right block. So I would try to compute it. So the left end would be equal to start plus 1 into B. How it's equal to start plus 1 into B? If you have solved 2-3 problems of square root decomposition, it becomes pretty intuitive. So if you are at a block and you want to know its end, if you know the starting of this block, which is block 0, if you know the starting of this block, you know the starting number of this block, after how many things would you have this ending block? So 0 plus B, right? 0 plus B. This block has B elements. So 0 plus B would give you the end of this block. So start, if it's 0, only if it's 0, start only if it's 0, would give you this thing. Otherwise, if you want to know the actual index, of the start, you need to figure out B into start, isn't it? If this wasn't 0, if it was somewhere here, there are B elements before it. So it's B into start. So b into start plus b is equal to b into start plus b is nothing but start plus 1 into b. So that's how you write it. Okay. So the left hand is clear. Left hand is clear. How to figure out the left hand? Okay. Next, what else do I need to figure out? So I also need to find out the right hand, but before that, let's brute force from left to left hand. That means this part. We need to brute force this part. So starting from left to left hand, I less than or equal to left and I plus plus blocks of start what was it, y of I minus minus, if it becomes 0, blocks of start y of I, if it becomes a 0, just erase. Actually I can copy this from here. So the brute force code would never change in most cases. Okay, so that's it. And now coming to the other thing, which is this part. We need to compute the right start. How to compute the right start? And right start it would be equal to end into b, isn't it? Right start would be equal to end into b. So similarly, how this got start into b, because start block was somewhere here, and before start block there would be b into start blocks. Start block was this, so b into start would be the preceding elements. Like there in the previous blocks there were b into start elements. Now to compute this thing, the start of this one, before this there are b into end elements. This block is end block, which is partially taken. So before this block there are end into b elements. So you have the index of right start now. So for int I equal to right start, I less than or equal to r, I plus plus. This time we need to do the same brute force again, but one small change is because we are at end block, we need to make this as end here as well. End, yeah. And left is fine, right is fine. The partial things we have encountered. Now what about the blocks in between? Okay, so what have we done is, there was a partial block here. We have computed this part, because L started from here and R ended here. What about the blocks in between? I already told you we are not gonna compute things for this. So what I would do is simply I would do from start plus 1, it's not a partial block. Start is a partial block, end is a partial block. Start plus 1 is not a partial block. Okay, from start plus 1 to end minus 1, that means less than n, it's not a partial block. So what I can do is I can add this to lazy of I. That means these blocks have a plus 5 or plus some val. Okay, these blocks have a plus val. Fine, we have computed left partial block, we have computed right partial block, and the blocks in between can be computed using this lazy thing. Fine. Till here the first query is clear. The first query is clear, which is of type add. The next type is type 2 query. So if it's a type 2 query, int total would be at query of 1. Int total would be at query of 1. Now we need to count something. What was it? Number of pairs. We were supposed to count number of pairs. I guess this is also some sort of two-sum variant. It's also some sort of a two-sum variant where you count the number of pairs. It's very easy, not that tough. So auto ampersand value 1 from, you're taking this from the first array, which we didn't modify. Okay, we were supposed to perform add operation only on the second array. Okay, you're picking v1 from first array and you are iterating over the k blocks. Okay, let's take a better variable name, block equal to 0, block less than total number of blocks, which is k, and block plus plus. And what are you supposed to find? What is your target? You have a total, which is your target. You need to check for pairs which make up to this total, and you already have v1 in your hands. That means the required total is total minus v1 so far. And you need to search for some target in the unordered map. I already told you real value is equal to stored plus lazy. Okay, real value is equal to stored plus lazy. I only have these stored values in the unordered map. That means real value which I need to find, stored value which I need to find is real minus lazy, which is equal to stored value. Okay, real minus lazy equal to stored value. That means if this whole thing is the real value, total minus v1 is the real value which I need to find. Int real target, real is total minus v1. And the thing I need to find is real minus lazy. Actual target which would be stored in the unordered map. The data structure would be real minus lazy of block. Fine. Now I would find it simply. Auto it equal to blocks of block dot find. What I need to find? I need to find the target, which is a representation of the stored value, not the real value. It's the stored value. If the stored value is available, which is if it is not equal to blocks of block dot end, if it is not equal to blocks of block dot end, count plus equal to it second, which is the frequency of that particular thing. So if v1 from some nums 1 can pair with v2 which is in nums 2, and v2 appears 3 times, so this v1 can pair with this v2, this v2, this v2. That means there are 3 pairs. So that's why we are adding this count here. Fine. Now once this is done, after this for loop, what you will do? You would do a simple answer dot pushback. I'm unable to find the right parentheses. What do you say, curly brace or something? Yeah. So I guess this is it. Answer dot pushback, and you need to push back this count. Fine. And finally return answer. Mr. Semicolon, block number, where is it? A variable type. Okay, it's not left, it's L. Few typing mistakes and variable name typos. Yeah. I could have coded it a bit faster without proper explanation. And it doesn't pass. Did we miss something? Did we miss something? Let's add this test case and let's look for did we miss something. So the thing is n equal to y size, b equal to square root of n plus 1, n plus b minus 1 by b, which is the seed. Fine. Unordered map int blocks of size k, lazy k comma 0, int block number would be equal to I by b, which is also fine, and block of block number. Actually, we could have used block number. That's not an error, but still, we are declaring a variable and not using it. So vector int answer auto ampersand query in queries. Type would be in query of 0. Type equal to 1. We'll take r equal to query of 1 or l val. Fine. Start equal to l by b. End equal to r by b. If start equal to end, what are you supposed to do? L to r, I plus plus, blocks of start, yi minus minus. If it becomes 0, erase it. Yi plus equal to y, blocks of start, yi plus plus. Otherwise, you would compute left hand, which is start plus 1 into b. I equal to l. I less than or equal to left hand. This is the issue. Okay, this is the issue. I should be less than left hand. Fine. I should be less than or equal to left hand. Fine. Maybe that's the only issue. Let's see. Okay, this case also, the extra case also passes. Okay. Signed integer overflow. And it happened here. Y of I plus equal to val. There's a signed integer overflow here. Are we storing garbage value somewhere? Okay, so far where have we checked? I've checked till L equal to, sorry, I equal to L, I less than left hand, I plus plus, blocks of start by I minus minus. If blocks of 1, erase it. Y plus equal to 1, for int I equal to 0, sorry, start plus 1, I less than n, I plus plus, and lazy of I plus equal to y, right start equal to n into b. From right start to, am I still getting recorded? From right start to less than or equal to r, I plus plus. Why would it give a integer overflow? First thing, what is y of I? What is y of I? It shouldn't be giving integer overflow no matter what, isn't it? Adding a small value isn't supposed to give integer overflow. So, what can I do? Why is it giving an integer overflow? Okay, so how about converting this to long long? But still it isn't supposed to give integer overflow. Or maybe it can. Can long long handle this? Don't think so. So after a while of debugging, I think we should make this yi as long long. So let's name it something else, nums2 only. And is there a better way to make an array completely long long? Except for doing this vector long long. Y is equal to nums2. Okay, so it gives an error for sure. So let's use some extra time for this. Auto ampersand I M Y, sorry, nums2. Y dot push back I into another. Fine. That's all we can do. and once again integer overflow. Let's make this long then. Let's make everything long. Done. Yeah, so that was the thing. I hope the square root decomposition part is clear, except for that debugging and all, which is very easy. The error was pretty intuitive, right? It was just an integer overflow. We had to change a few stuff. That's it. So thank you everyone. However, I took a little 5 minutes more for debugging, but acceptable because if I completely mess up, then the 1 hour duration of the video would get wasted. I have to record again from the start. Okay, so probably I would take a cut of those 5 minutes which I debug. That's not actually technically debugging because there's nothing to learn from there, right? Isn't it? There's nothing to learn from there. So it's just integer to long thing. So thank you everyone.